Hi everyone, welcome to this video looking at calculations from balanced equations that involve gases. This is connected to the learning outcomes that we went through last day when we were looking at the molar volume of a gas and how it can be determined. And we should also know that molar volume is dependent on temperature and pressure. Okay, so today we're moving on to I can perform calculations given a balanced equation using data including gram formula masses and masses, if we're talking about a solid, number of moles, which could be any state of matter, concentrations and or volumes of solutions, and then when we're talking about gases, molar volumes and volumes. This is just part one, I suppose, of this learning outcome. Today we're going to be looking at when we're given a balanced equation and some things are gases and some things are not, and we use our knowledge of mole relationships to calculate the quantities that the question asks for. Okay, so the next two slides are for writing down in our notes jotter. So throughout National 5 and higher, we have learned how to calculate number of moles using these relationships. So we've got number of moles is concentration times the volume, so that we sometimes put that in this kind of triangle relationship. Okay, and that just shows us how to manipulate it. So if we want to know concentration, we would do number of moles divided by volume and so on. We should also be able to calculate number of moles from mass divided by the gram formula mass. So that one looks like this. Number of moles is the mass divided by the gram formula mass. And then number of moles is volume divided by the molar volume. Okay, so I just want to highlight what the appropriate units should be in each case. Okay, so anytime we've got number of moles, we can just write that as MOL, or in full would just be moles. Concentration is in moles per litre, and volume is in litres. Okay, mass is in grams, and number of moles again is in moles. Gram formula mass, it would be grams per mole, but we usually just leave it blank, or I suppose technically we could write atomic mass units, but we don't need to worry too much about the units for that. Volume is in litres, number of moles is in moles, and molar volume would be in litres per mole. Okay, so we can now use these relationships along with the mole ratio from a balanced equation to calculate quantities in a given reaction. We should pay particular attention to the units, especially if there is a conversion required. For example, centimetre cubed to litres. Okay, we might be given a volume in centimetres cubed and we would need to convert it to litres before we manipulate it in an equation. Okay, so that's the theory. I have 6 examples for you that we're going to write out together. So what you might find useful is if you pause the video before I start going through it to give you a chance to copy down the question, or I suppose you could print out the slides from the PDF and annotate them, or if you're using a tablet, you could just annotate the slides directly. But the most important thing is that you can follow the procedure for calculating the desired quantity. Okay, so here is example 1. So I'm going to use a highlighter so that I know what information from the question is important. So when sodium hydrogen carbonate is heated to 112 degrees, it decomposes and the gas carbon dioxide is given off. Calculate the theoretical volume of carbon dioxide produced by the complete decomposition of 1.68 grams of sodium hydrogen carbonate. Take the molar volume of carbon dioxide to be 23 litres per mole. So from my balanced equation, I am concerned about the sodium hydrogen carbonate and the carbon dioxide. And the information I have about the sodium hydrogen carbonate is that I've got 1.68 grams of it. I have a mass, okay? And I've also got a molar volume for the carbon dioxide, which is 23 litres per mole. Okay, so first step I'm going to do, because I've already been given a balanced equation, is I'm going to put my mole ratio. So the mole ratio would be 2 to 1, okay? Because I've got 2 moles of the sodium hydrogen carbonate and 1 mole of the carbon dioxide in the balanced equation. So I need to work out now how many moles do I actually have. So for the sodium hydrogen carbonate, it's a solid and I know what the mass is. So I'm going to start off by working out the number of moles I actually have. And I do that with the mass over gram formula mass relationship. Now, in the exam, if you were given a formula like this, you would probably be given what the gram formula mass of it is, but we can calculate it. So for 1 mole of sodium hydrogen carbonate, the mass is actually 84 grams. Okay, so the mass would be 1.868 grams divided by the gram formula mass, which is 84. You can work that out just to make sure I'm right. 23 plus 1 plus 12 plus 48. And we get an answer of 0.02 moles. Okay, then we're going to use our mole ratio. So we know that 2 moles gives us 1 mole. So 2 moles of sodium hydrogen carbonate gives us 1 mole of carbon dioxide. So what would 0.02 moles give us? So according to the mole ratio, 2 would give 1. So 0.02, which we actually have, is going to give 0.01 moles. Okay. We are asked to calculate a volume. That's what the question is really about. So I calculate volume using number of moles multiplied by the molar volume. Number of moles is 0.01 from here, and the molar volume is 23. So the answer is going to be 0.23 litres, or 230 centimetres cubed, depending on what you're asked for it in. Okay, so that would be our final answer. Let's look at example 2. Magnesium reacts with 1 mole per litre hydrochloric acid to form hydrogen. Here's the balanced equation. If excess magnesium is added to 50 centimetre cubed of 0.2 mole per litre acid, what volume would be produced if the molar volume of hydrogen is 24 litres per mole? Okay, so let's just use our highlighter to make sure that we know what information we need from the question. So we've got, we know the magnesium is in excess. Oh dear, there's a wee mistake in this question. I'm very sorry about this. This should not say this here. So if excess magnesium is added to, here's a volume and here's the correct concentration of acid, what volume would be produced if the molar volume of hydrogen is 24 litres per mole? Okay, so I'm concerned about the hydrochloric acid and the hydrogen. The magnesium is in excess, okay, so I don't need to worry about how much of that I've got. Okay, so let's look at the mole ratio then. It's going to be 2 to 1, okay? So we work out how many moles of hydrochloric acid do we actually have, and we do that by doing C times V, which is 0.2 from the question, and 50 centimetre cubed, which is going to be 0.05 litres, and that is 0.01 moles. Okay, so from the mole ratio, 2 moles would give us 1 mole. 2 moles of hydrochloric acid would give us 1 mole of hydrogen. So 0.01 moles is going to give us 0.005 moles. Now that I know how many moles I've got, I want to work out the volume, and I do that by volume is the number of moles multiplied by the molar volume. So number of moles is 0.005, and the molar volume, according to the question, is 24. So the answer is going to be 0.12 litres, or 120 centimetres cubed. Example 3. One of the methods used to synthesize urea is to react ammonia with carbon dioxide. The balanced equation for this process is shown here. We carry out this reaction by combining 7.5 grams of ammonia and 4.5 litres of carbon dioxide, and the molar volume is 25 litres. Calculate the limiting reagent. Okay, so the first step of this, I need to look at the ammonia and the carbon dioxide. So I need to look at the ratio of the reactants to work out which is in excess. Okay, so the mole ratio of the reactants is 2 to 1. Let's work out how many moles of each I actually have. So for the ammonia, The number of moles is the mass divided by the gram formula mass. So we've got 7.5 according to the question. So that's 7.5 divided by 17, because it's NH3 would be 14 plus 3. And that is 0.44 moles. For the carbon dioxide, it's a gas, and we're told we've got 4.5 litres of it. So we work out the number of moles is the volume divided by the molar volume. So 4.5 divided by 25, and that is 0.18 moles. So now we need to work out which one is limiting. So we've got this 2-to-1 ratio. Okay, 2-to-1 ratio. Now, if all of the 0.44 moles of ammonia reacted, then we would need half of that. So this would need 0.22 moles of carbon dioxide. But we only have 0.18 moles. If 0.18 moles of the carbon dioxide reacted, it would need twice that, so that would be 0.36, which is less than what we've got available, so that would be fine. So the limiting reagent is the carbon dioxide, and that's because if all of the ammonia reacted, it would need 0.22 moles, and we only have 0.18, and that is according to the molar ratio. So I'm just going to write down that 0.44 moles of ammonia requires 0.22 moles of carbon dioxide, only 0.18 moles available, therefore carbon dioxide is limiting. Okay, that means it is controlling how much product can be generated. It's the limiting reagent. Okay, so ammonia is in excess, carbon dioxide is limiting. Now, if we know that the carbon dioxide is limiting, we can use that to work out the mass of urea that is produced. So that's for part B of this question. So now we've got to look at a new mole ratio. So we look at the ratio between the carbon dioxide and the urea, and it's a 1-to-1 ratio. It's a 1-to-1 ratio, and we know that we've got 0.18 moles of carbon dioxide. Let's find it over here. So we're going to get 0.18 moles of urea. Now, urea, let's look at this. Urea has a gram formula mass of 60. You could calculate that, but that's what it is. And if I calculate this, then the mass would be the number of moles times the gram formula mass, which is 0.18 times 60, and that is 10.8 grams. Okay, so that would be our final answer for this question, 10.8 grams. We've worked out the mass of urea produced from our balanced equation. Question 4, so I've not really left enough space to put question numbers, but never mind. The explosive RDX is used in the controlled demolition of disused buildings. During the reaction, it decomposes as shown. Calculate the volume in litres of gas released when 1 gram of RDX decomposes. Take the molar volume of the gases to be 24 litres per mole. So we've got 1 gram of RDX, and we've told the molar volume. Now, this question is quite unusual because we actually have all of our products are gases, and we've got 9 moles of gases in this question in the reactants. So if we're to look at the mole ratio, now, just to be clear, we know the Molar Gas Laws tells us that 1 mole of a gas occupies the same volume as 1 mole of any other gas. So a mole of carbon monoxide is going to occupy the same space as a mole of water vapour, which is going to occupy the same space as a mole of nitrogen. So we can actually just say that 1 mole of the RDX is going to give us 9 moles, that's the total, 9 moles of gas. Okay? So let's work out how many moles of RDX we actually have. Number of moles is mass divided by the gram formula mass. Again, we're not going to spend time looking at calculating gram formula mass, but you can do this in your own time. It's 222 grams. So we've got 1 over 222, which comes out as a horrible number. 0.00450, so on. So that's if 1 mole gives 9 moles of gas, then 0.0045 and so on moles would give us 9 times that, which would be 0.040540 moles. So that's how many moles of gas we're going to get. The question asks us calculate the volume of gas we're going to get. So we work that out by doing volume is number of moles multiplied by the molar volume. So this number here, 0.04054 multiplied by 24, which is 0.97 litres, or 970 centimetres cubed. Okay, so that's that question. Question 9 then. Hydrogen sulfide gas can be... question 9. What am I talking about? Question 5. Hydrogen sulfide gas can be prepared by the reaction of iron 2 sulfide with excess dilute hydrochloric acid. So we've got our balanced equation here, and we're asked to calculate the mass in grams of iron sulfide required to produce 79 centimetre cubed of hydrogen sulfide gas. So first thing I'm going to do, again, highlight the important information. So the mass of iron sulfide required to produce 79 centimetres cubed of hydrogen sulfide gas. And I've got the molar volume. So the mole ratio is 1 to 1. And I can work out, firstly, I've got to start with my product here, because I'm asking how much of the iron sulfide, the reactant, is going to be required. So to work out the number of moles of hydrogen sulfide that we start with, we're going to need to do number of moles is volume divided by the molar volume, which is, okay, so I've got to change the 79 into 0.079 litres. So 0.079 divided by 24, which is about 0.0033. I'm just going to double check that on my calculator. No, I've missed out a 0. Good job I checked. Oh no, have I? No, I put in an extra 0. Never mind. 0.079, that's my volume, divided by 24, and it's 0.0033. Yes, super. So that's the number of moles of gas that I get produced. If the ratio is 1 to 1 of the iron sulfide to the hydrogen sulfide, then if I produce 0.0033 moles, then I can start with 0.0033 moles. That's what I would need to give me that mass. Now that's, to give me that volume. Now I need to work out the mass, which is mass is number of moles times the gram formula mass. So 0.0033 multiplied by the gram formula mass of iron sulfide is 87.9. Again, you can work this out. It's just the iron is 55.8 plus the sulfur, which is 32.1. So pop those numbers into your calculator, and we get 0.2893 so on grams, which is approximately 0.3 grams. Okay, so that's the mass I would require at the start. Right, our final example then. We have, in spacecraft, the total mass carried and air quality are important. Lithium hydroxide has been used to absorb carbon dioxide produced by astronauts. The equation for the reaction is shown. Okay, so I have 6 grams of lithium hydroxide, and that is going to absorb 5.9 litres of carbon dioxide. And I'm asked to work out molar volume. So this is something we've not done before in these examples, but we'll just use exactly the same relationships and technique. So it's a 1-to-1 ratio of reactants. So let's find out how many moles of lithium hydroxide we actually have. So we do that in the same way. Number of moles is mass divided by gram formula mass. So that's 6 over 24, because lithium would be 7 plus 16 plus 1 is 24. And that comes out as 0.25 moles. So because it's a 1-to-1 ratio, then 0.25 moles would react with 0.25 moles. And I know that I've got 5.9 litres. Okay, so I've got a volume and I've got a number of moles. So I calculate molar volume by doing the volume divided by the number of moles, which is 5.9 litres divided by 0.25 moles, and that is 23.6 litres. And that really looks like a molar volume that we would be used to. We've seen some that are like 22, 23, 24, 25. So that's a clue that we're on the right track for this question. Okay, that is the final example. If you've managed to copy down all 6 examples, then you deserve a wee break and a cup of tea before you start anything else, okay? It's really important that you feel confident with these type of calculations, because you'll see that as we've gone through them, we've used exactly the same relationships each time. We just manipulate them according to what we're required for that question. So hopefully you managed okay with this. If you need anything else, please just let us know. We're all here to help you. Okay, take care everyone.